The dawn of time. The history of the universe begins with an event so monumental, so transformative, that it shaped the very fabric of existence, the Big Bang. About 13.8 billion years ago, everything we know, galaxies, stars, planets, and even space and time, exploded out of an unimaginably small, infinitely dense point known as a singularity. However, this explosion was not an explosion in the conventional sense, but an expansion, an unimaginably rapid expansion of space itself. In the first trillionth of a second, the universe expanded exponentially, growing from smaller than an atom to the size of a galaxy. This is what cosmologists call cosmic inflation, a theory that helps explain the incredible uniformity we observe in the cosmic microwave background radiation, the faint afterglow of the Big Bang. During this early phase of expansion, the temperature of the universe was so high that particles as we know them could not exist. Instead, it was a bubbling soup of pure energy, governed by the laws of quantum mechanics. As the universe cooled down, just fractions of a second later, elementary particles such as quarks and gluons began to form. These quarks would later combine to form protons and neutrons, the building blocks of atomic nuclei. This was the beginning of matter as we understand it, a process driven by the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces. But even in these early moments, the seeds of the future structure of the universe were sown. Small fluctuations in the density of this primordial soup, caused by quantum uncertainty, would eventually produce the cosmic structures we see today. These density fluctuations, reinforced by gravity, formed the galaxies, stars, and planets that populate the universe. It is a humbling thought that the vast structures of the cosmos were born from the tiniest, barely perceptible ripples in space-time. Let us pause for a moment and reflect on the nature of the singularity from which the universe emerged. Put simply, a singularity is a point in space at which the forces of gravity become infinite and the laws of physics as we know them fail. This is not just a scientific curiosity, but a profound philosophical challenge. If all the mass and energy of the universe was once compressed into this point, what does that tell us about the nature of space and time before the Big Bang? Some scientists believe that time itself could not have existed before the Big Bang. In this view, the question of what was before the Big Bang is meaningless, as time only began with the Big Bang. Others propose more exotic theories, such as the possibility that the Big Bang was not the beginning of everything, but merely a transition, a bouncing from a previous contracting universe. This idea is part of what is known as the cyclical universe theory, which states that the universe goes through endless cycles of expansion and contraction. The singularity remains one of the greatest mysteries of cosmology, a place where our current understanding of the universe, based on Einstein's general theory of relativity, fails. It's a puzzle that may require a new theory of quantum gravity that unites the principles of general relativity with the strange, probabilistic world of quantum mechanics. Cosmic inflation is one of the key ideas that explain why the universe looks the way it does today. Without inflation, we would expect the universe to be much more chaotic, with large differences in temperature and density from one region to another. Instead, we see a cosmos that is remarkably homogeneous on large scales, with only small fluctuations that eventually led to the formation of galaxies. The theory of inflation was first proposed in the 1980s by the physicist Alan Guth, who assumed that the universe underwent a phase of extremely rapid expansion in the first fraction of a second after the Big Bang. This inflationary period smoothed out all the irregularities in the early universe and explains why the cosmic microwave background radiation, the oldest light in the universe, looks so uniform when we observe it. But cosmic inflation does not only explain the uniformity of the universe, it also provides a framework for understanding the origin of the universe itself. In some versions of inflationary theory, the universe could be part of a much larger multiverse, with inflation occurring in different regions of space at different times. This leads to the intriguing possibility that our universe is just a bubble in a vast sea of other universes, each with its own unique physical laws and constants. What if inflation had never happened? Imagine for a moment that inflation never happened. What kind of universe would we live in today? Without inflation, which smoothed out the initial conditions of the Big Bang, the universe would probably be much more chaotic. Instead of the relatively even distribution of matter that we see today, there would be vast regions of empty space interspersed with dense clumps of matter. Stars and galaxies could still form, but they would be distributed irregularly and disorderly. The cosmic microwave background radiation would also look very different, with large temperature fluctuations from one region to another. This chaotic universe would be a far cry from the orderly, structured cosmos we inhabit. Inflation not only gave us a smooth, homogeneous universe, but also enabled the formation of the large-scale structures we see today. The tiny density fluctuations that existed in the early universe were stretched by inflation, and these fluctuations later became the seeds for galaxies and galaxy clusters. In a universe without inflation, these fluctuations might never have grown large enough to form galaxies, and the universe might be a much emptier and lifeless place. The age of particles. As the universe continued to cool down after the Big Bang, a new chapter in its history began. The age of particles. This era, which began just seconds after the birth of the universe, is the time when the basic building blocks of matter, particles such as quarks, electrons, and neutrinos, came together to form the shapes we know today. This period, which lasted only a few minutes, laid the foundation for the formation of atoms, stars, and galaxies billions of years later. In the first moments after the Big Bang, the universe was so hot that particles could not exist in their stable form. Instead, the universe was a quark-gluon plasma, a hot, dense soup of quarks, the particles that make up protons and neutrons, and gluons, the particles that mediate the strong nuclear force. Quarks exist in 6 different types, or flavors: up, down, strange, charm, top and bottom, but in the earliest moments of the universe they were freely mobile and not yet bound in protons and neutrons. Leptons, another class of fundamental particles, also moved freely during this time. The best-known lepton is the electron, but there are also others, such as muons and tauons, and their associated neutrinos. Neutrinos play a decisive role in this early universe. These ghostly particles, which interact only weakly with matter, were produced in large numbers in the first seconds of the universe and are still present today, whizzing through space and through us at almost the speed of light. As the universe cooled further, the quarks began to bind and form protons and neutrons. This process, called hadronization, took place in the first microseconds of the universe's existence. Protons and neutrons are known as hadrons, composite particles consisting of quarks. This marks the transition from the quark-gluon plasma to the particle-dominated universe we know today. One of the great mysteries of cosmology is why there is more matter than antimatter in the universe. According to the laws of physics, matter and antimatter should have been created in equal quantities in the early universe. But when matter and antimatter collide, they annihilate each other and generate pure energy in the form of photons. So why didn't the universe end up as a sea of radiation without matter? This question is at the heart of what is known as baryogenesis, the process by which an asymmetry between matter and antimatter emerged in the early universe. While the exact mechanism of baryogenesis is still unknown, scientists believe that it must have taken place in the first fractions of a second after the Big Bang. During this time, some processes must have slightly favored the production of matter over antimatter, eventually leading to the matter-dominated universe we see today. One of the central theories behind baryogenesis involves CP violation, a subtle asymmetry in the laws of physics that governs the behavior of particles and their antiparticles. Under normal circumstances, the laws of physics should be the same for matter and antimatter. However, experiments have shown that this is not always the case. Under certain conditions, particles and antiparticles behave slightly differently. This CP violation may have shifted the balance in favor of matter, so that enough matter survived annihilation with the antimatter to form the stars and galaxies we see today. One of the most remarkable discoveries in modern cosmology is the existence of the cosmic microwave background radiation, CMB, a faint afterglow of the Big Bang that permeates the entire universe. Discovered in 1964 by Arno Penzias and Robert Wilson, the CMB provides a picture of the universe as it was 380,000 years after the Big Bang, long before the first stars and galaxies were formed. The CMB is amazingly even, with only tiny temperature deviations in the sky. These temperature fluctuations, which are of the order of 1 part in 100,000, reflect the density fluctuations in the early universe that eventually grew into galaxies and galaxy clusters. By studying the CMB, scientists have been able to learn a lot about the early universe, including its age, composition, and geometry. The CMB also contains references to the inflationary period that took place in the first fractions of a second after the Big Bang. Inflation extended the tiny quantum fluctuations in the early universe to macroscopic sizes, and these fluctuations left their imprint on the CMB. By analyzing the CMB in detail, cosmologists have been able to test different models of inflation and learn more about the nature of the early universe. What if there were no asymmetry between matter and antimatter? Imagine a universe in which the symmetry between matter and antimatter was perfect. In this scenario, matter and antimatter would have been created in exactly equal quantities in the first moments after the Big Bang. As the universe cooled, these particles would have collided and annihilated each other, leaving nothing but radiation. In this alternative universe, there would be no stars, no planets, and no life. Just an endless sea of photons, remnants of matter-antimatter annihilation. The universe would still be expanding, but it would be a sterile, lifeless place. In fact, the concept of matter would be meaningless, as no matter would exist at all. The fact that our universe contains more matter than antimatter is one of the most important mysteries of modern physics. Without this asymmetry, the universe would be a completely different place without the complexity and structure that we see around us. The first 3 minutes after the Big Bang were crucial for the creation of the elements that make up the universe. During this time, the temperature of the universe dropped from trillions to just over 1 billion degrees, cool enough for protons and neutrons to combine to form the nuclei of simple elements such as hydrogen, helium, and a small amount of lithium. This process is known as Big Bang nucleosynthesis. At these high temperatures, nuclear reactions took place quickly, but they lasted only a few minutes before the universe became too cool for nuclear fusion to continue. As a result, only hydrogen and helium were produced in significant quantities, with traces of lithium and beryllium. Heavier elements, such as carbon, oxygen, and iron, had to wait billions of years to be formed in the cores of stars. The relative abundances of hydrogen and helium that were created during Big Bang nucleosynthesis can still be observed today. About 75% of ordinary matter in the universe is hydrogen, while 25% is helium, with only traces of heavier elements. This composition is a direct result of the conditions that prevailed in the first 3 minutes of the history of the universe. Imagine a universe in which Big Bang nucleosynthesis would not have produced helium. In this scenario, the only element present in the early universe would be hydrogen, the simplest and most common element. While stars could still form from hydrogen gas, their structure and evolution would be very different. Helium plays a crucial role in the life cycle of stars, especially in the later stages of stellar evolution. Without helium, stars would be less stable and would use up their hydrogen fuel much faster. The absence of helium would also affect the production of heavier elements, as helium is a key element in the nuclear reactions that produce elements such as carbon and oxygen in the cores of stars. In this hypothetical universe, stars would be shorter-lived and less capable of producing the elements necessary for life. Planets like Earth, which are rich in heavier elements, could never form, and the universe would be a much simpler and less diverse place. The Dark Ages of the universe. After the intense activity of the first few minutes, the universe entered a period known as the Dark Ages. This epoch, which lasted from about 380,000 years to a few 100 million years after the Big Bang, is called the Dark Ages. Not because it was inherently dark, but because no stars or galaxies had yet formed to light up the universe. At that time, the universe was filled with neutral hydrogen gas, and the only light that existed was the cosmic microwave background radiation, CMB, too weak and too uniform to produce visible structures. This era was crucial in creating the cosmic structures we see today, but it is also shrouded in mystery. Understanding the Dark Ages is crucial to understanding how the first stars and galaxies formed and how they reionized the universe, ending the Dark Ages and ushering in the cosmic dawn. As the universe expanded, it continued to cool. About 380,000 years after the Big Bang, it cooled down enough for protons and electrons to combine to form neutral hydrogen atoms. This process is known as recombination, although the name is somewhat misleading. This was the first time that protons and electrons combined, so technically it was not a recombination. The formation of neutral atoms was a significant milestone in the evolution of the universe. Before recombination, the universe was filled with a hot, dense plasma of charged particles that made it opaque to light. Photons, particles of light, could not travel far without being scattered by electrons, much like light has difficulty passing through a dense fog. But after recombination, the universe became transparent, allowing light to travel freely for the first time. This release of photons, known as decoupling, is what we observe today as cosmic microwave background radiation. The CMB is a snapshot of the universe as it was shortly after recombination, showing us a picture of the universe when it was only a few 100,000 years old. But with the formation of neutral hydrogen, the universe was shrouded in darkness. No stars had yet formed to illuminate the universe, and the light from the CMB had been stretched into the microwave region of the spectrum, making it invisible to the naked eye. Although the universe was dark at this time, it was by no means empty. The density fluctuations that had been sown during the inflationary period continued to grow under the influence of gravity, forming the framework for what was to become the large-scale structure of the universe. These density fluctuations in the matter content created a cosmic web of filaments and voids in which matter was concentrated in some regions and almost completely absent in others. This cosmic web was to become the foundation for the formation of galaxies and galaxy clusters. The dense regions of the web, where gravity was strongest, attracted more matter and eventually collapsed to form the first stars and galaxies. Meanwhile, the less dense regions became the vast cosmic voids that separate the galaxy clusters today. During the Dark Ages, this cosmic web was still in its infancy, and the matter within it consisted mainly of neutral hydrogen and dark matter. Dark matter, which interacts neither with light nor with ordinary matter except through gravity, played a crucial role in the formation of the cosmic web. In fact, dark matter is thought to make up about 85% of the total mass of the universe, and its gravitational influence helped pull ordinary matter into the dense regions of the web. The role of dark matter in the evolution of the universe is one of the most fascinating mysteries of modern cosmology. Although we cannot see or directly detect dark matter, its presence can be deduced from its gravitational effects. For example, the rotational speeds of galaxies cannot be explained by visible matter alone. There must be a large amount of invisible mass holding them together. We call this invisible mass dark matter. During the Dark Ages, dark matter was crucial in shaping the universe. It formed the gravitational wells into which ordinary matter, mainly hydrogen gas, could fall. Without dark matter, the density fluctuations in the early universe might not have been large enough to form galaxies. The ordinary matter that interacts with light and other forms of radiation would have been too hot and too diffuse to collapse on its own. Scientists are still trying to understand the exact nature of dark matter. One of the leading candidates is a class of particles known as weakly interacting massive particles, WIMPs, which would interact only through gravity and the weak nuclear force. Another possibility is actions, extremely light particles that could solve some of the mysteries of quantum chromodynamics, the theory that describes the strong nuclear force. Despite decades of searching, no direct evidence of dark matter particles has yet been found, but their gravitational influence is undeniable. What would the universe look like if there was no dark matter? In this scenario, the ordinary matter in the universe, hydrogen gas, would still be present, but it would find it difficult to form large structures. Without the gravitational pull of dark matter, the small density fluctuations in the early universe would not be enough to cause the gas to collapse into stars and galaxies. Instead, the universe would remain a vast, featureless sea of diffuse gas. There would be no galaxies, no stars, and no planets, just an endless sea of hydrogen atoms drifting through space. The universe would continue to expand, but it would be a cold, dark, and lifeless place. In this mind game, the absence of dark matter would mean the absence of structure, and the universe would be far less interesting. Dark matter is not just a theoretical curiosity, it is a fundamental part of the architecture of the universe. Without them, the cosmos would be a completely different and much more boring place. The Dark Ages ended with the formation of the first stars, a period known as the Cosmic Dawn. These stars, known as population 3 stars, were unlike any stars that exist today. They were massive, hot, and short-lived, composed almost exclusively of hydrogen and helium, the only elements that existed at that time. The population 3 stars were the first objects in the universe to produce light since the cosmic microwave background radiation came into existence. Their formation marked the beginning of the Rayonization era, when the ultraviolet light from these early stars ionized the surrounding hydrogen gas by removing electrons from the atoms and allowing the light to travel freely again. These first stars were also responsible for the creation of the first heavy elements. Through the process of nuclear fusion, the population 3 stars transformed hydrogen and helium into elements such as carbon, oxygen, and iron. When these stars reached the end of their short lifetimes, they exploded into powerful supernova, scattering these heavy elements into space. This process, known as nucleosynthesis, is the mechanism by which all elements heavier than hydrogen and helium were formed. Imagine a universe in which the first stars never formed, and heavy elements such as carbon and oxygen were never formed. In this universe, the only existing elements would be hydrogen and helium. While stars could still form from these elements, they would be much simpler and less diverse than the stars we see today. More importantly, planets like Earth, which are rich in heavy elements, would never form. Life as we know it is dependent on heavy elements. Carbon forms the basis of organic chemistry, and elements such as oxygen, nitrogen, and phosphorus, are crucial for the biochemical processes of life. Without these elements, complex life would probably be impossible. In this mind game, the universe would be a sterile place, without planets, without life, and without diversity of matter. The formation of heavy elements by the first stars was a crucial step in the evolution of the cosmos, enabling the richness and complexity we see today. As more and more stars formed, their ultraviolet light began to ionize the universe again. This process took hundreds of millions of years and was probably driven not only by stars, but also by the first galaxies and quasars, extremely bright, active galactic nuclei powered by supermassive black holes. Reionization transformed the universe from a dark, neutral place into the bright, transparent cosmos we see today. The reionization era was the last major phase in the evolution of the universe before the formation of large-scale structures such as galaxies and galaxy clusters. During this time, the universe was completely ionized so that light could travel freely, and the universe became transparent to radiation. By the end of reionization, about 1 billion years after the Big Bang, the universe had taken on its modern form, with stars, galaxies, and the cosmic web all fully formed. The formation of galaxies and stars. When the universe left its dark era behind and entered the era of reionization, the stage was set for one of the most profound transformations in cosmic history, the formation of galaxies and stars. In this chapter, we will examine the processes that led to the formation of these fundamental cosmic structures and the roles they play in shaping the universe we observe today. As we discussed in the previous chapter, the universe is structured like a giant cosmic web, with dense filaments of dark matter and normal matter stretching through space and connected by vast, empty voids. The formation of this cosmic web was driven by gravity, which pulled matter into ever denser regions, eventually leading to the formation of the first stars and galaxies. The cosmic web is not just a theoretical construct, it is something we can observe. In recent decades, astronomers have mapped the distribution of galaxies across the sky, and they see a universe in which galaxies are not randomly scattered, but are arranged along giant filaments, with clusters of galaxies forming at the intersections of these filaments. This large-scale structure of the universe, known as the cosmic web, is the direct result of the density fluctuations that existed in the early universe. Dark matter plays a decisive role in the formation of the cosmic web. Since dark matter interacts only through gravity, it clumped together more easily than normal matter, creating the gravitational wells into which gas and dust eventually fell to form galaxies. Without dark matter, the process of galaxy formation would have been much slower, and the universe would look very different today. The first galaxies began to form about 1 billion years after the Big Bang during the epoch of reionization. These early galaxies were much smaller and less massive than the galaxies we see today, but they played a crucial role in the evolution of the universe. By collecting gas and dust into dense regions, these early galaxies created the conditions necessary for the formation of stars, the engines of cosmic evolution. Galaxies are formed through a process known as hierarchical merging. In this model, small structures, so-called proto-galaxies, formed first, which in the course of time merged with other proto-galaxies to form larger and more complex galaxies. This process is still taking place today. When we observe the universe, we see galaxies colliding and merging on all scales. One of the main characteristics of early galaxies is their intense star formation. These galaxies, composed mainly of hydrogen and helium, were sites of rapid star formation, producing stars at a much higher rate than we see in modern galaxies. This period of rapid star formation is known as the starburst phase and played a decisive role in shaping the chemical composition of the universe. Stars are the fundamental building blocks of galaxies, and the process of star formation is one of the most important mechanisms driving the evolution of the universe. Stars are formed by the gravitational collapse of clouds of gas and dust known as molecular clouds. These clouds, which can span hundreds of light years, contain enough material to form thousands of stars. The process of star formation begins when a region of a molecular cloud becomes dense enough for gravity to overcome the pressure of the gas and the cloud collapses. As the cloud collapses, it breaks up into smaller clumps, each of which will eventually form a star. When the gas collapses, it heats up, and the temperature in the center of the collapsing cloud rises to millions of degrees. When the temperature gets high enough, nuclear fusion ignites in the nucleus and a star is born. The mass of a star determines its fate. Small stars, like our Sun, slowly burn up their hydrogen supply over billions of years before eventually becoming red giants and shedding their outer layers, creating a dense remnant known as a white dwarf. Larger stars, on the other hand, burn their fuel much faster and end their lives in spectacular supernova explosions in which they eject their outer layers into space, leaving behind either a neutron star or a black hole. Stars are also the engines of chemical evolution in the universe. Through the process of nuclear fusion, stars convert hydrogen into heavier elements such as helium, carbon, and oxygen. When these stars die, they eject these elements into space, enriching the interstellar medium with the building blocks necessary for the formation of planets and life. In this way, stars are responsible for creating the elements that make up everything we see around us, from the oxygen we breathe to the carbon in our bodies. At the center of most galaxies, including our Milky Way, there is a supermassive black hole. These cosmic giants, with masses millions to billions of times greater than the Sun, are among the most mysterious and awe-inspiring objects in the universe. How they are formed and what role they play in the evolution of galaxies is still the subject of intensive research. One of the leading theories states that supermassive black holes are formed by the collapse of massive gas clouds in the early universe. Over time, these black holes grew by accreting gas and merging with other black holes until they reached the enormous masses we see today. Observations of distant quasars, extremely bright, active galactic nuclei powered by supermassive black holes, indicate that these objects existed just a few 100 million years after the Big Bang, suggesting that the formation of black holes is closely linked to galaxy formation. Supermassive black holes play a crucial role in regulating star formation in galaxies. material falls into a black hole, it heats up and emits enormous amounts of energy in the form of radiation and jets of high-energy particles. These outflows can heat up the gas in the surrounding galaxy and prevent it from cooling down and forming new stars. In this way, black holes act as a feedback mechanism and regulate the growth of galaxies by preventing them from becoming too large. The Milky Way, home to our solar system, is a spiral galaxy that was formed billions of years ago through the process of hierarchical merging. Over the course of its long history, the Milky Way has grown through the accretion of gas and stars from smaller galaxies, and this is still happening today. In fact, the Milky Way is currently merging with several smaller galaxies, including the Sagittarius Dwarf Galaxy and the Large and Small Magellanic Clouds. The structure of the Milky Way is typical of spiral galaxies. It has a central bulge in which the stars are densely packed, and a disk in which stars, gas, and dust form spiral arms. The galaxy also has a halo of older stars and globular clusters orbiting the disk, as well as a massive dark matter halo that extends far beyond the visible galaxy. Dark matter, which makes up the majority of the galaxy's mass, plays a crucial role in holding the galaxy together and preventing it from flying apart. At the center of the Milky Way is a supermassive black hole called Sagittarius A. Although relatively quiet at present, Sagittarius A occasionally flares up and emits bursts of radiation as it accumulates material from its surroundings. The presence of this black hole is evidence that supermassive black holes are a common feature of galaxies and may play an essential role in their formation and evolution. What will happen to the Milky Way in the distant future? Astronomers have long known that the Milky Way is on a collision course with the nearby Andromeda Galaxy, the largest galaxy in our local group. This collision, which will take place in about 4 billion years, will dramatically reshape both galaxies. Instead of a violent collision, the two galaxies will slowly merge over the course of several billion years, with their stars and gas clouds interacting gravitationally to form a new, larger galaxy. When the Milky Way and Andromeda collide, their supermassive black holes will also merge, forming an even more massive black hole at the center of the newly formed galaxy. This process will release enormous amounts of energy, possibly triggering a burst of star formation as the gas clouds of both galaxies are compressed by the collision. The life and death of stars. Stars are the fundamental engines of the universe. They drive everything from the formation of planets to the synthesis of heavy elements that form the building blocks of life. Understanding how stars are born, live and die gives us crucial insights into the cosmic processes that have shaped the universe since the first stars ignited over 13 billion years ago. In this chapter, we will examine the life cycle of stars, the different paths they take depending on their mass, and the spectacular ways they end their lives. Stars are formed in huge clouds of gas and dust known as molecular clouds or stellar nurseries. These clouds, which sometimes extend over hundreds of light years, consist mainly of hydrogen, as well as small amounts of helium and traces of heavy elements. Within these clouds, certain regions become dense enough for gravity to overcome the gas pressure, leading to the collapse of the cloud and the formation of a protostar. The process of star formation is a delicate balance between gravity, which pulls the gas inwards, and pressure, which counteracts collapse. As the cloud collapses, it heats up, and the gas in the center of the collapsing cloud becomes incredibly hot and dense. When the temperature in the core of the protostar reaches around 10 million degrees, nuclear fusion ignites and hydrogen atoms begin to fuse to form helium. This marks the birth of a star. The fusion of hydrogen to helium in the core of a star releases enormous amounts of energy, which counteracts gravity and prevents the star from collapsing further. This energy is emitted as light, and it is this light that makes stars visible to us. Stars spend most of their lives in this stable phase, known as the main sequence, during which they fuse hydrogen in their cores to form helium. The life of a star in the main sequence is mainly determined by its mass. More massive stars burn their hydrogen supply much faster than smaller stars. For example, a star like our Sun will remain in the main sequence for about 10 billion years, while a more massive star, 10 times the mass of the Sun, will use up its fuel in just a few million years. However, smaller stars, known as red dwarfs, can remain in the main sequence for hundreds of billions of years. During the time in the main sequence, a star is in a state of hydrostatic equilibrium. This means that the pressure exerted by the fusion reactions in the nucleus balances out the inward force of gravity. This delicate balance enables the star to shine evenly for billions of years. But once the star has used up the hydrogen in its core, it has to find new ways to generate energy, which leads to significant changes in its structure and behavior. Imagine a universe in which nuclear fusion never takes place. Without fusion, stars could not generate the energy needed to resist gravitational collapse and would quickly decay into cold, dark objects. The universe would lack the light and warmth provided by the stars, which would make life as we know it impossible. Furthermore, without fusion, stars could not produce the heavy elements necessary for the formation of planets and life. In this alternative universe, the cosmos would be a much simpler place, without stars, galaxies, and planets. The only source of energy would be the faint glow of the cosmic microwave background radiation, the afterglow of the Big Bang. The absence of fusion would fundamentally change the nature of the universe and prevent the formation of the complex structures we see today. For stars like our Sun, the end of their life comes when they run out of hydrogen for fusion in the core. When this happens, the core contracts and heats up, while the outer layers of the star expand. This causes the star to swell into a red giant, a phase in which the star can grow hundreds of times larger than its original size. In this phase, the star begins to fuse helium in the core to form carbon and oxygen. Eventually, the helium also runs out, and the star is no longer able to generate enough energy to support itself. The outer layers of the star are ejected into space and form a beautiful gaseous envelope known as a planetary nebula. The now exposed core continues to contract until it becomes a dense remnant known as a white dwarf. White dwarfs are incredibly dense objects with a mass equal to that of the Sun, but in a volume the size of the Earth. A single teaspoon of white dwarf matter would weigh several tons. White dwarfs no longer produce energy through fusion, but they continue to glow faintly as they slowly cool over billions of years. Eventually, they cool down so much that they no longer emit visible light and become black dwarfs, although the universe is not yet old enough for black dwarfs to exist. While low-mass stars like the Sun end their lives quietly as white dwarfs, more massive stars perish in a glorious inferno. When a massive star uses up the hydrogen and helium in its core, it begins to fuse heavier elements such as carbon, oxygen, and silicon. This process continues until the core of the star consists almost entirely of iron. Unlike lighter elements, which release energy during fusion, iron does not produce energy through fusion. As a result, the core can no longer support the weight of the star, and it collapses under its own gravity. This collapse happens incredibly quickly, within seconds, and triggers a huge explosion known as a supernova. The outer layers of the star are ejected into space, while the core is compressed into an incredibly dense object called a neutron star. Neutron stars are even denser than white dwarfs. Just one sugar cube full of neutron star material would weigh as much as a mountain. These stars consist almost entirely of neutrons, which are so densely packed that the core of the star is only about 20 kilometers in diameter, but can have a mass greater than that of the Sun. Supernovae are not only spectacular explosions, but are also responsible for the creation of many of the heavy elements in the universe. Elements heavier than iron, such as gold, silver, and uranium, are produced under the extreme conditions of a supernova and scattered into space, where they can be incorporated into new stars and planets. In this way, supernovae play a decisive role in the chemical evolution of the universe. For the most massive stars, even the formation of a neutron star is not enough to stop the collapse of the core. In these cases, the nucleus continues to collapse until it forms a black hole, an object so dense that not even light can escape its gravitational pull. Black holes are some of the most mysterious and fascinating objects in the universe and test our theories of physics. The boundary around a black hole, beyond which nothing can escape, is known as the event horizon. Once an object crosses this boundary, it is destined to be pulled into the singularity at the center of the black hole, where the laws of physics as we know them break down. Black holes can be formed by the collapse of massive stars, but they can also grow by absorbing material from their surroundings or merging with other black holes. Black holes are often portrayed as cosmic vacuum cleaners that suck up everything around them, but the reality is a little more nuanced. The gravitational force of a black hole is no stronger than that of the star from which it was formed. So objects that were far enough away from the star continue to orbit the black hole as they did before with the star. But anything that gets too close is drawn in and cannot escape. Imagine a universe in which there are no black holes. In this scenario, the most massive stars would still end their lives in supernova explosions, but instead of collapsing into black holes, their cores would either become neutron stars or disintegrate completely. Without black holes, many of the extreme phenomena we observe in the universe, such as quasars and gravitational waves, would not exist. Black holes play an important role in the formation of galaxies. Their immense gravity can influence the orbits of stars and gas clouds, and their powerful energy beams can regulate star formation. Without black holes, galaxies could develop very differently, and the large-scale structure of the universe could be altered. In this thought experiment, the absence of black holes would also have profound implications for our understanding of fundamental physics. Black holes are laboratories for studying the extreme effects of gravity and quantum mechanics, and they challenge our understanding of space and time. Without them, many of the most exciting questions in modern physics would remain unexplored. Stars are not only the engines of energy in the universe, they are also responsible for producing the chemical elements that make up everything around us. Through the process of nuclear fusion, stars produce elements such as carbon, oxygen, and iron, which are then scattered into space when the stars die. These elements are incorporated into new stars, planets, and ultimately into life. This process, known as stellar nucleosynthesis, is the primary mechanism by which the universe was enriched with heavy elements. The early universe, as we have already discussed, consisted almost entirely of hydrogen and helium, with only small traces of other elements. Over billions of years, stars have transformed these simple elements into the complex array of elements we see today, from the carbon in our bodies to the silicon in computer chips. Supernovae and the violent deaths of massive stars play a particularly important role in this process. The extreme temperatures and pressures in a supernova explosion enable the formation of elements heavier than iron, which cannot be produced inside stars. These heavy elements are then hurled into space, where they are incorporated into new generations of stars and planets. Imagine a universe in which stars cannot produce heavy elements. In this scenario, the only elements that exist would be hydrogen and helium, along with traces of lithium and beryllium from the Big Bang. Without elements such as carbon, oxygen, and nitrogen, the chemistry of life would be impossible. Planets like Earth, which are rich in heavy elements, would never form, and the universe would be a much simpler, less diverse place. In this alternative universe, stars could still form and shine, but they would not go through the complex life cycles that lead to the formation of planetary systems and the chemical diversity necessary for life. The absence of heavy elements would fundamentally change the nature of the universe and make it a much less interesting and habitable place. The death of a star marks the beginning of its journey to the stellar graveyard. Depending on its mass, a star can end its life as a white dwarf, neutron star, or black hole. These remnants are some of the most extreme objects in the universe and offer a glimpse into the final stages of stellar evolution. White dwarfs, as already mentioned, are the remnants of low-mass stars such as the Sun. These dense, dim objects cool slowly over billions of years and eventually become cold, dark remnants known as black dwarfs. Neutron stars, on the other hand, are the remnants of more massive stars that have undergone supernova explosions. These incredibly dense objects consist almost entirely of neutrons and have intense magnetic fields that can generate powerful bursts of radiation. Black holes, the most extreme objects in the stellar graveyard, are the remnants of the most massive stars. These objects bend space-time so much that not even light can escape their gravity. While black holes are often invisible, their presence can be detected by their effects on neighboring matter, such as the accretion of gas or the gravitational influence on nearby stars. The formation of planetary systems. While stars are the primary energy suppliers and chemical evolutionary engines in the universe, planets provide the stage for complex chemistry and ultimately for life. The formation of planetary systems is a natural side effect of star formation, and understanding how planets form and evolve is crucial to understanding the conditions necessary for life to emerge. In this chapter, we will examine the process by which planets form from the leftover material around a newborn star, the diversity of planetary systems in the universe, and the potential for life beyond Earth. When a star is born, it is often surrounded by a rotating disk of gas and dust known as a protoplanetary disk. This disk is a byproduct of the star formation process, as not all of the material from the collapsing cloud is integrated into the star. Instead, this leftover material forms a disk around the young star from which planets, moons, asteroids, and comets eventually form. The formation of planets begins with tiny grains of dust within the protoplanetary disk. These grains, which consist of elements such as carbon, silicon, and oxygen, adhere to each other through electrostatic forces and form ever larger clumps. Over time, these clumps grow into planetesimals, objects that are several kilometers in size. The gravity of these planetesimals enables them to attract even more material, which leads to the formation of protoplanets. As these protoplanets grow, they begin to clear their orbits and pick up smaller debris that gets in their way. The process of planet formation can take millions of years and depends on several factors, including the mass of the protoplanetary disk, the distance to the star, and the interactions between the growing planets. In some cases, planets can migrate from their original positions, leading to dramatic rearrangements of planetary systems. Imagine a universe in which planetary systems never form. In this scenario, stars do exist, but they are only surrounded by diffuse clouds of gas and dust, without planets, moons, or asteroids. Without planets, there would be no environments in which complex chemical processes could take place, and the emergence of life as we know it would be impossible. In this alternative universe, the cosmos would be a much simpler place, with no planets or moons to explore. The great variety of planetary systems that we observe today, from Earth-like rocky planets to gas giants like Jupiter, would not exist. The absence of planets would also mean that the complex gravitational interactions between planets, moons, and their parent stars would be absent, making the universe a much less dynamic place. In our own solar system, the formation of the gas giants Jupiter and Saturn played a decisive role in shaping the architecture of the planetary system. Gas giants are thought to form through a process called core accretion, in which a massive protoplanet, consisting mainly of rock and ice, becomes large enough to attract a dense shell of hydrogen and helium from the surrounding protoplanetary disk. Gas giants such as Jupiter and Saturn form relatively quickly because they have to collect their thick atmospheres before the protoplanetary disk dissolves. The presence of gas giants can have a significant influence on the formation of other planets in the system. For example, Jupiter's powerful gravitational pull is thought to have influenced the orbits of the smaller, rocky planets in the inner solar system, as well as the distribution of asteroids and comets. In other planetary systems, gas giants can form much closer to their parent stars, forming so-called hot Jupiters that orbit their stars in just a few days. The discovery of these hot Jupiters in the 1990s challenged existing theories of planet formation, as it was previously thought that gas giants could only form far away from their stars, where the temperature is low enough for hydrogen and helium to condense. The discovery of hot Jupiters led to new models of planetary migration, in which gas giants can move inwards or outwards from their original positions. While gas giants dominate the outer regions of many planetary systems, the inner regions are often home to smaller rocky planets such as Earth, Mars, and Venus. These planets are formed from the rocky material left behind in the protoplanetary disk, and they are usually much smaller and denser than gas giants. The formation of rocky planets involves a process called oligarchic growth, in which a few large protoplanets dominate their local regions of the disk, picking up smaller planetesimals and growing larger over time. As these planets grow, they can collide with other protoplanets, which can lead to the formation of moons or the loss of planetary atmospheres. The presence of water and other volatile compounds is crucial for the development of life on rocky planets. It is believed that in the early solar system, icy comets and asteroids brought water from the outer regions of the system to the inner planets, including Earth. The availability of water and the right chemical ingredients on a rocky planet can create the conditions necessary for the development of life. Since the first discovery of an exoplanet, a planet orbiting a star outside our solar system, in the 1990s, astronomers have discovered thousands of these distant worlds. Exoplanets come in an astonishing variety of sizes, compositions, and orbits that go far beyond what we see in our own solar system. Some exoplanets are gas giants, like Jupiter and Saturn, while others are smaller, rocky worlds like Earth. Some orbit their stars at distances much closer than Mercury's orbit around the Sun, while others are in the cold outer regions of their systems. There are also super-Earths, planets with masses between that of Earth and that of Neptune, which could have dense atmospheres or liquid water on their surface. One of the most exciting fields of exoplanet research is the search for habitable worlds, planets that are in the habitable zone of their stars, where temperatures are just right for liquid water to exist. Although no direct evidence of life on an exoplanet has yet been found, the discovery of potentially habitable worlds raises the possibility that life could exist elsewhere in the universe. Imagine a universe in which only gas giants form and rocky planets like Earth never appear. In this scenario, planetary systems would exist, but they would be composed exclusively of massive gas giants, with no smaller rocky worlds that could provide stable surfaces for life. While gas giants could have moons, it is unlikely that these moons offer the same potential for life as Earth-like planets. Without rocky planets, the diversity of planetary systems would be greatly reduced, and the potential for life as we know it would be much lower. The lack of solid surfaces would make it difficult for complex chemical processes to take place, and the extreme conditions on gas giants, characterized by high pressure and extreme temperatures, would be inhospitable for most life forms. This thought experiment underlines the importance of rocky planets in the search for life beyond Earth. While gas giants play a crucial role in shaping planetary systems, it is the smaller, rocky worlds that provide the environments necessary for life to evolve. One of the most profound questions in science is whether there is life elsewhere in the universe. The discovery of thousands of exoplanets has broadened the search for life beyond our solar system, and scientists are now investigating the conditions that could make a planet habitable. For a planet to be considered potentially habitable, it must fulfill several criteria. Firstly, it must be in the habitable zone of its star, where the temperatures are suitable for liquid water to exist. Secondly, it must have a stable atmosphere that can regulate the temperature and protect the surface from harmful radiation. After all, it must have the right chemical ingredients for life, including carbon, hydrogen, oxygen, nitrogen, and phosphorus. Although Earth is the only known planet on which life exists, there are several promising candidates for habitability in our solar system. Mars, for example, shows evidence of liquid water in the past, and scientists are investigating whether microbial life may still exist beneath its surface. Europa and Enceladus, moons of Jupiter and Saturn, have underground oceans that could possibly support life. The mysteries of dark matter and dark energy. While much of what we know about the universe comes from observing stars, galaxies, and planets, two profound mysteries continue to elude us: dark matter and dark energy. Together, these invisible forces account for most of the mass and energy of the universe, but we can neither see them nor detect them directly. In this chapter, we will look at what we know and what we don't know about dark matter and dark energy, their roles in shaping the cosmos, and how they challenge our knowledge of physics. Dark matter makes up about 85% of the total mass of the universe, but it does not emit, absorb, or reflect light, making it invisible to telescopes. Their existence was first suspected in the 1930s by the Swiss astrophysicist Fritz Zwicky, when he observed that the galaxies in the Coma cluster were moving too fast to be held together by visible matter alone. Zwicky hypothesized that there must be an invisible mass, dark matter, that provides the additional gravitational force needed to prevent the galaxies from flying apart. Since then, dark matter has been detected indirectly through its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. For example, when astronomers observe the rotation curves of galaxies, i.e., how fast stars move at different distances from the center of the galaxy, they find that stars that are far away from the center move much faster than the amount of visible matter can explain. This discrepancy can only be explained by the presence of a dark matter halo surrounding the galaxy. But what exactly is dark matter? Scientists have proposed several candidates, but the most likely are weakly interacting massive particles, WIMPs. These hypothetical particles would only interact through gravity and the weak nuclear force, which makes them extremely difficult to detect. Despite numerous experiments designed to detect WIMPs directly, this has not yet been achieved, so the true nature of dark matter remains one of the greatest unsolved mysteries of modern physics. Let us imagine a universe in which dark matter does not exist. In this scenario, galaxies would not have enough mass to hold themselves together, and the stars at the edges of the galaxies would drift out into space. The large-scale structure of the universe would be far less organized, as dark matter plays a crucial role in the formation of galaxy clusters and the cosmic network. Without dark matter, the universe would probably be a much more chaotic place with fewer galaxies and less structure. Stars could still form, but the complex patterns of filaments and voids that we see in the cosmic web would not exist. In this thought experiment, the absence of dark matter would fundamentally change the architecture of the universe, making it a less coherent and more diffuse place. Dark matter is not just an invisible force. It plays an active role in the formation of galaxies and galaxy clusters. In the early universe, tiny fluctuations in the density of dark matter created gravitational wells into which normal matter, gas, and dust could fall, eventually leading to the formation of galaxies. Without dark matter, these fluctuations would not have been large enough to grow into the massive structures we see today. Simulations of the early universe that include dark matter show how these gravitational sinks allowed galaxies to form relatively quickly after the Big Bang. Dark matter also helps to explain the distribution of galaxies in the cosmic web, as it provides the framework on which the galaxies are built. Even today, dark matter influences the evolution of galaxies by helping to hold them together and preventing them from flying apart. One fascinating aspect of dark matter is that it only interacts with normal matter through gravity. This means that dark matter does not collide with or influence normal matter as ordinary particles do. Instead, it acts as an invisible scaffold that shapes the universe on a large scale without interacting directly with the particles that form stars, planets, and galaxies. While dark matter holds galaxies together, dark energy drives them apart. Discovered in the late 1990s through observations of distant supernovae, dark energy is the driving force behind the accelerated expansion of the universe. Previously, astronomers assumed that the expansion of the universe was slowing down due to the force of gravity. However, observations have shown that the expansion is actually accelerating, which points to the existence of a previously unknown force, dark energy. Dark energy is thought to make up around 70% of the total energy content of the universe, making it the dominant force shaping the cosmos. However, like dark matter, dark energy is also extremely difficult to grasp. It does not interact with normal matter in any detectable way, and its exact nature remains one of the greatest mysteries of cosmology. One of the leading theories on dark energy is that it is a property of space itself, known as the cosmological constant. In this view, dark energy is a form of vacuum energy that permeates all of space and pushes galaxies apart as the universe expands. Another theory suggests that dark energy could be a dynamic field that evolves over time, similar to how electromagnetic fields work. However, no definitive proof of either theory has yet been found, so the nature of dark energy remains an open question. Let's explore the future of the universe in a scenario where dark energy continues to drive accelerated expansion. Over billions of years, the galaxies will move further and further apart until they are finally so far apart that they are no longer visible from Earth or any other vantage point. The night sky, once filled with countless stars and galaxies, is becoming increasingly empty as the light from distant galaxies is redshifted beyond the visible spectrum. In this big freeze scenario, stars will continue to burn their nuclear fuel, but without the birth of new stars, the universe will gradually become darker and colder. Over time, black holes will dominate the cosmos, but they too will eventually evaporate through a process called Hawking radiation, leaving behind a universe consisting only of a diffuse sea of low-energy particles. This thought experiment illustrates the profound influence of dark energy on the fate of the universe. Although we now live in a universe full of galaxies, stars, and planets, dark energy ensures that this state is only temporary. Over the next tens of billions of years, the universe will become an increasingly desolate place as the galaxies move further and further apart. What was Einstein's biggest mistake? The idea of a cosmological constant, an energy density that fills space evenly, was first proposed by Albert Einstein in 1917 as a way to compensate for the gravitational collapse of the universe. At the time, astronomers believed that the universe was static, neither expanding nor contracting, and Einstein introduced the cosmological constant into his equations of general relativity to maintain this equilibrium. But when Edwin Hubble discovered in the 1920s that the universe was expanding, Einstein rejected the idea of the cosmological constant and called it his biggest mistake. However, with the discovery of dark energy in the 1990s, the cosmological constant was once again taken up as a possible explanation for the accelerated expansion of the universe. In modern cosmology, the cosmological constant remains one of the leading candidates for dark energy, although its exact value and origin are still the subject of intense research. If the cosmological constant is indeed responsible for dark energy, this raises profound questions about the nature of space and time and why the universe has the specific energy density that it does. Now imagine a universe in which dark energy does not exist. In this scenario, the expansion of the universe would be determined solely by gravity and the initial conditions of the Big Bang. Over time, the expansion would slow down, and in some models, the universe could even begin to contract again, leading to a big crunch in which all matter and energy are compressed back into a hot, dense state, possibly triggering a new Big Bang. In a universe without dark energy, the galaxies would remain closer together, and the large-scale structure of the universe would be much more compact. The ultimate fate of the universe in this scenario would depend on its total mass and energy. If the universe contains enough mass, it would eventually collapse in a big crunch, while a lower mass universe could continue to expand forever, albeit much more slowly than we observe today. The evolution of the universe. The universe, from its chaotic birth in the Big Bang to its present state with structured galaxies and stars, has undergone an incredible development. Each phase of cosmic evolution was characterized by striking events that influenced the formation of galaxies, stars, planets, and ultimately also life. In this chapter, we explore the key phases of the evolution of the universe from the earliest moments after the Big Bang to the distant future, and consider how the universe might continue to change over the coming billions of years. As we have already discussed, the first few minutes after the Big Bang were decisive in shaping today's universe. At that time, the universe was incredibly hot and dense, filled with a plasma of particles such as protons, neutrons, electrons, and photons. During this period, nucleosynthesis took place, creating the light elements, hydrogen, helium, and traces of lithium, that make up most of the normal matter in the universe. These elements formed as the universe rapidly expanded and cooled. Protons and neutrons fused to form helium nuclei, but the temperature dropped too quickly to form heavier elements. The resulting composition, about 75% hydrogen and 25% helium by mass, remains in the universe today, with heavier elements being produced much later in stars. This phase prepared the ground for the entire future cosmic evolution. Since the universe was still hot and dense, radiation dominated matter, and photons constantly interacted with the particles, preventing the formation of atoms. The universe was a chaotic, glowing plasma of particles and radiation, and it took hundreds of thousands of years for the first atoms to form. After the formation of the first atoms through recombination, the universe entered a phase known as the Cosmic Dark Ages, which lasted from around 380,000 years to several hundred million years after the Big Bang. In this era, neutral hydrogen dominated the universe and no light sources such as stars or galaxies had yet formed. Although the universe was filled with matter, it was dark and without recognizable structures. While the universe was dark, gravitational forces were already at work. Tiny density fluctuations sown during cosmic inflation began to grow under the influence of dark matter. These fluctuations would eventually become the gravitational sinks in which the first stars and galaxies were formed. The Dark Ages were a period of silent expectation, a time when the universe waited for the first light sources to shine. This era ended with the formation of the first stars, an event that marked the beginning of the Rayonization era and brought about the first significant changes in the structure of the universe. The Rayonization era began when the first stars and galaxies formed, about 500 million years after the Big Bang. These early stars were massive, hot, and short-lived, burning up their hydrogen supply quickly and emitting intense ultraviolet radiation. This radiation ionized the surrounding hydrogen gas by splitting electrons from the atoms and transforming the once neutral gas into an ionized plasma. The process of rayonization was not instantaneous. It took hundreds of millions of years for the entire universe to be fully rayonized. During this time, the light of the early stars and galaxies gradually penetrated the darkness of the cosmic dark ages, and the universe began to take on its present form, with bright galaxies and stars illuminating the void. Rayonization was a decisive step in cosmic evolution, as it allowed light to move freely through space. Before reionization, the universe was opaque to ultraviolet light, much like fog blocks visibility in all directions. After the universe was rayonized, light from distant galaxies and stars was able to travel through the cosmos, allowing us to observe them today. With the completion of reionization, the universe entered a phase of rapid growth and evolution as galaxies and galaxy clusters were formed by the gravitational collapse of dark matter and gas. Over the next billions of years, galaxies continued to grow and evolve, merging with each other to form the large-scale structures we see today. The process of galaxy formation is influenced by both dark matter and normal matter. Dark matter, which makes up the majority of the mass of the universe, provides the gravitational scaffolding on which galaxies are formed. As dark matter clumps together, it creates gravitational sinks that attract gas, dust, and stars, leading to the formation of galaxies. Without dark matter, the structure of the universe would be much less organized, and galaxies would not have formed in the same way. Clusters of galaxies, large groups of galaxies held together by gravity, also began to form during this time. These clusters can contain thousands of galaxies and are some of the largest structures in the universe. The interactions between galaxies and clusters can lead to spectacular collisions and mergers that drive the evolution of galaxies over billions of years. At the center of most galaxies, including our Milky Way, are supermassive black holes with masses millions to billions of times that of the Sun. These black holes play a crucial role in the evolution of galaxies, as their enormous gravitational force influences the orbits of stars, gas, and dust in the galaxy. In addition, the energy released by infalling material can regulate star formation and prevent galaxies from becoming too large. One of the most dramatic phenomena associated with supermassive black holes is the formation of quasars, extremely bright, active galactic nuclei that are powered by the accretion of material onto the black hole. Quasars were much more common in the early universe, and they give us an insight into the violent processes that shaped galaxies in the past. When material falls into the black hole, it heats up and radiates enormous amounts of energy that can outshine entire galaxies. Although quasars are rare today, supermassive black holes continue to play an important role in the evolution of galaxies. By regulating star formation and influencing the distribution of gas and dust, black holes contribute to the structure and behavior of galaxies over billions of years. When we look at the universe on the largest scales, we see that galaxies are not randomly distributed. Instead, they are arranged along huge filaments of matter separated by enormous empty spaces. This large-scale structure of the universe is known as the cosmic web and is one of the most striking features of the cosmos. The cosmic web is shaped by the distribution of dark matter, which forms the backbone of the structure of the universe. Over billions of years, dark matter has agglomerated into dense filaments and created the gravitational sinks that are home to galaxies. The voids between these filaments are regions of space where dark matter and normal matter are sparse, resulting in vast, empty regions between the galaxy clusters. The cosmic web provides a framework for understanding how galaxies and clusters of galaxies are distributed in the universe. It also provides clues to the nature of dark matter, as the distribution of dark matter is responsible for the large-scale structure we observe. By studying the cosmic web, astronomers can learn more about the underlying physics that governs the evolution of the universe. While the universe has been expanding since the Big Bang, the discovery of dark energy in the late 1990s revealed that this expansion is not slowing down, as previously assumed, but is actually accelerating. Dark energy, which makes up about 70% of the total energy of the universe, is the mysterious force responsible for this acceleration. The exact nature of dark energy remains one of the greatest mysteries of cosmology, but its effects are undeniable. As dark energy drives the expansion of the universe, galaxies are moving further and further apart, and the accelerated expansion has profound implications for the future of the universe. The fate of the universe. As we explore the distant future of the cosmos, the question arises, what will the ultimate fate of the universe be? In recent decades, cosmologists have developed several theories about how the universe could develop over the next billions and trillions of years. These theories depend on a combination of factors, including the nature of dark energy, the amount of matter in the universe, and the laws of physics itself. In this chapter, we will examine the various scenarios for the end of the universe, including the Great Freeze, the Great Rift, and the Great Collapse. The most widely accepted theory about the future of the universe is the Big Freeze, also known as heat death. This scenario is based on the observation that the universe is expanding at an increasing rate due to the influence of dark energy. As the galaxies move further and further apart, the universe becomes emptier and emptier, and the energy available for physical processes decreases. In the Great Freeze scenario, the expansion of the universe continues indefinitely, and over time, all energy sources, such as stars, will have used up their fuel. Stars will go out, leaving behind cold, dead remnants such as white dwarfs, neutron stars, and black holes. In the next billion years, even the longest-lived stars will go out, and the universe will become darker and darker. As the universe expands, the galaxies will move so far apart that they will no longer be visible to each other. The cosmic background radiation, the last remnant of the Big Bang, will continue to redshift as the universe expands, eventually disappearing altogether. Without the formation of new stars, and without remaining energy sources, the universe will enter a state of thermodynamic equilibrium in which all matter and energy are evenly distributed and no more work can be done. This state is referred to as heat death, as the universe will be essentially cold and lifeless. In this scenario, black holes could be the last remaining objects in the universe, but they are not eternal either. Over time, through a process called Hawking radiation, black holes will gradually lose mass and give off tiny amounts of energy as they slowly evaporate. Eventually, all black holes will completely evaporate, and the universe will be cold and empty, filled with a thin, diffuse soup of low-energy particles. This marks the final fate of the universe in the Great Frost scenario, a cold, dark, and lifeless expanse. Imagine the universe in the distant future, tens of trillions of years from now, when the last red dwarf stars are slowly using up the last of their hydrogen fuel. Red dwarfs are the longest-lived stars in the universe, with lifetimes spanning trillions of years. In the distant future, these faint, cool stars will be the last sources of light in an otherwise dark universe. As the universe continues to expand and cool, even these long-lived stars will eventually die out. Without the energy of starlight, planets, if they still exist, will freeze, and the remaining life will face a cold, harsh reality. The death of the last stars will mark the beginning of the final phase of the evolution of the universe as all energy sources are exhausted. This mind game highlights the profound loneliness and desolation of the distant future, when the universe becomes a vast, empty space, with no new stars, no galaxies, and no light to illuminate the darkness. Another possible fate of the universe is the Great Rift, a scenario in which dark energy becomes stronger and stronger over time and eventually tears apart galaxies, stars, planets, and even atoms. This theory is based on the idea that dark energy is not constant, but could increase in strength as the universe expands. In the Great Rift scenario, the accelerated expansion of the universe driven by dark energy continues, and the rate of expansion becomes so extreme that it overcomes the gravitational forces holding galaxies, stars, and planets together. First, galaxies are torn apart as their stars are flung apart. Next, individual solar systems, including stars and their planets, will be torn apart by the ever-increasing expansion. If the expansion continues to accelerate, the forces holding atoms and subatomic particles together will eventually be overcome, leading to the disintegration of all matter at the smallest scales. The universe would end in a violent and dramatic way, with everything, galaxies, stars, planets, and even atoms, being torn apart by the inexorable expansion. The timing of the Great Rift depends on the properties of dark energy. If dark energy becomes stronger over time, the Great Rift could occur in the distant future, perhaps tens of billions of years from now. However, current observations suggest that dark energy behaves like a cosmological constant, which means that the Great Rift may not be the ultimate fate of the universe. Nevertheless, it remains a possibility that cosmologists continue to investigate. Imagine what it would be like to experience the final moments of a universe heading towards the Great Rift. First, the galaxies would begin to stretch and tear apart, with stars being hurled into the dark void between the galaxies. With the increasing expansion, the gravity that holds solar systems together would weaken, and planets would be torn away from their stars. Eventually, even the stars themselves would be torn apart, their atoms torn apart by the unstoppable expansion. In the final moments before the Big Rip, even atoms and subatomic particles would be torn apart, leaving only radiation and energy. The universe would end in a chaotic, violent dissolution without any structure or order being able to survive. This mind game underscores the dramatic and destructive nature of the Great Rift scenario, in which even the most basic building blocks of matter are torn apart. In contrast to the Big Freeze and Big Rip scenarios, the Big Crunch represents the possibility that the expansion of the universe will eventually slow down and reverse, leading to a collapse of all matter and energy into a hot, dense state. This theory depends on whether the amount of matter in the universe is sufficient to stop the expansion and trigger a gravitational collapse. If there is enough matter in the universe, both normal matter and dark matter, gravity could eventually overcome the expansion and bring galaxies, stars, and planets closer together. Over billions of years, the universe would shrink, become hotter and denser, while matter and energy would be compressed. Eventually, the universe would reach a state similar to the initial conditions of the Big Bang, with all matter and energy concentrated in a single point. The Great Collapse could possibly trigger a new Big Bang, which would lead to a cyclical model of the universe in which the cosmos goes through endless cycles of expansion and contraction. In this model, the universe is not a one-off event, but a continuous process of creation and destruction in which each cycle brings forth new galaxies, stars, and planets. Although the Great Collapse was once considered the leading theory for the fate of the universe, the discovery of dark energy and the accelerated expansion of the universe has reduced its probability. However, if dark energy weakens or reverses in the distant future, the Great Collapse could still be a possible outcome. Imagine living in a universe that is approaching the Great Collapse. Over time, the galaxies would move closer together, and the night sky would become brighter as more and more stars are packed into a shrinking volume of space. As the universe contracts, temperatures would rise and galaxies would merge, leading to intense star formation and violent collisions between stars and planets. In the final moments before the Great Collapse, the universe would become incredibly hot and dense, compressing all matter and energy into a tiny volume. Stars would explode in a final burst of energy, and black holes would merge into a single massive singularity. Eventually, the entire universe would collapse into a point of infinite density, setting the stage for a possible new cycle of expansion.